As always, we want to ensure that we have the most recent code from the repository. So let's do a git pull. Make sure that you're in your ATTC3260 folder. When I perform the git pull, I will grab any new code that has been published. All right, so we're up to date. Let's go ahead and open up Thony, and we will take a look at the code for lab 4.1.2. So here I already have this code up. I'm going to leave that up. If you don't have 4.1.1 open, go ahead and open that up, and we're going to do a comparison of the two. So if I come in here and I'm going to get it, just open up the 4.1.2 on the same page so that we can take a look at it there. Before we take a look at the code, our code's getting a little bit more complicated. In order to help us to understand what's happening, I'm going to turn on the line numbers. So we just went to Options and then do Show Line Numbers right here. And then when I select OK, now I have line numbers that I can take a look at and understand what line of code that I'm on. All right, the first 3 lines of code we've already seen. We've also seen the pin_r. The first line of new code in lab 4.1.2 is the assignment of the variable color options. And I just came up with a variable that made sense and described what I was trying to do. Here I am identifying the number of possibilities that we can make in an 8-bit number. You'll remember from previous videos that we could go from 0 to 255 and assign that number to the R or G or B pins, and that number would then make that specific color. So we're 256 because the 0 is also counted. I've made a block comment, so a comment with a bunch of dashes, so it makes it easier to identify where I'm creating the frequency. When we start setting up the green and blue frequency, we would continue to put this in this block, and it might make it a little easier to come back to and identify where that's happening at. The next thing that I'm doing is I'm creating a variable, and I'm giving the variable the name setRedColor. I'll also have a set green color and a set blue color in future code. This set red color is giving a value. That value is 25. Right now the LED, specifically the R pin, doesn't know what a 25 means. We're going to use some mathematical calculations to help the LED understand electrically what a 25 on a 0 to 255 scale means, and how do we electrically produce that. The next section has to do with setting the duty cycle. I've put it in blocks, and we will set the red, green, and blue duty cycle in this section. The first variable is a way for me to determine the amount of off time that the red LED circuit has. So if we recall, the circuit, the way that we have set it up is it is a low side driver. I'm using a transistor to turn on the ground side of the circuit. The circuit always has power. It's connected directly to the 3.3 volts. So the LED turns on when the circuit is off as far as its duty cycle. When the digital signal is low or close to 0, that will be when the circuit is complete. So I want to determine the red color based on the off time when the digital signal is low. When the digital signal is on, when it goes to high and it's close to 3.3 volts, the LED will turn off because there's no potential difference between the 3.3 volts created at pin R and the constant 3.3 volts at pin VCC. So let's take a look at the calculation that will be made for red color off time. First of all, red color off time will equal the value set red color, which in this case is 25. We'll divide that by color options, which we set that to 256. And then we want to multiply that by 100. The number that we will be getting is a percentage, so that's why we're multiplying it by 100. So if we take the 25 divided by 256, that will give us a value of 0.09765 and so on. Then when we multiply that by 100, we get a final value that will be assigned to red color off time of 9.765625. What that means is our digital signal off time is going to equal 9.77%. Now we need to be able to figure out the on time, because that's the value that we have to pass to the pulse width modulation. We have to pass it a duty cycle, and duty cycle is on time, not off time. So this next line of code is a variable that will be the duty cycle, the on time of this circuit. So here we have the red duty cycle. Signal duty cycle is assigned to a value of 100, which would represent a on time of 100%, and we're simply going to take away the 9.77% off time. So that's what we will set our duty cycle to. The value that will be set is 90.234. So that would then put our duty cycle at a 90.23%. Remember, that's the on time. The next 4 lines of code have already been used in previous examples. The final new statement is an additional print statement. I put this print statement in order for us to see at the console what values we are assigning to each of the variables. So the set R2 is just text that I've written. It will print that out. The plus is known as a concatenation. Concatenation means that I'm adding to the end of the statement. So it will say set R2, and then it will print out the value of set red color. Because set red color is an integer, I have to use the str command in order to change it into a string. And so I do the same thing for all the other values, and that will allow me to see what happens on the console when I execute this program. Open up a terminal and navigate to your Lab 4 folder. We'll execute Python, and we are working on Lab 4.1.2. So don't forget to put the .py on the end and hit the Enter button. When I press Enter, we should see the light illuminate, and we also see the dynamically populated statement printed in the terminal. That statement is showing me that I have set R to 25 on a scale of 0 to 255. The duty cycle or on time is 90.23, and the off time, which is when the ground is on, is 9.765.
Now we will set up the oscilloscope in order to measure the digital signal that we are sending out from the Raspberry Pi. In order to set up the oscilloscope, we will put a jumper wire on pin GPIO 17. Just put it in the same line as the white wire that we already have there. And then we will clip the oscilloscope probe to the other end. The other point that we will connect to is ground. You can get the ground anywhere. I've just got the ground down there at the bottom on pin 39, but any ground would be sufficient. And then I clip the ground lead on the jumper wire. Okay, turn on the oscilloscope, and we want to set our ranges. I went with 5 volts. 2 would probably be fine as well. And then my time I set at 100 microseconds. So that should give us a pretty good picture of the digital signal. Now that we have our oscilloscope set up to measure, you might see it scrolling across your screen really quickly. If you come down here to where my screen is showing the start, but yours will show the stop, if you select that, it will stop the signal so you can take a look at it by itself. Before we zoom in on the screen, let's recall how we designate the cycle. So there on the left, when the signal goes high, that is the beginning or start of the signal. The signal stays high for about 90% of the time, as we would expect, and then it drops to low. Once it goes low for 10% of that cycle, we have then the end of the cycle when the signal goes back up. Now remember, this cycle is continuously repeated and is the time based on it is the frequency that we have set. Now I'll zoom in on our cycle for the digital signal, and we'll look at one individual cycle by itself. In order to understand this measurement, we need to recall what the values were for our scales. So we set the voltage value to 5-volt scale. What that means is that each of these individual little squares represent 1 volt. And we're going in the vertical position. So if we stack up those squares going up that digital signal, our voltage value at high is 2.75 volts. As you recall, the time goes from left to right. So each of these small squares is a representation of 20 microseconds. You can see that slightly larger square that consists of 5 small squares. That represents the 100 microsecond scale that we have already set. We have 31 small squares going in through our cycle, and that adds up to 620 microseconds. That converts over to about 1700 hertz. Some of you may have noticed that your hertz is lower than expected. Our first value we set was 2000. And that has to do with the limitations of the Raspberry Pi in setting frequency. This is an extremely high frequency for such a small unit. We're now done with this lab, so go back to the terminal and press the Control-C. You'll notice that it will exit out of the program and then print the end of program statement.